We are going to see here how the Feynman theorem could be used in order to calculate the forces on the ions. So let's consider the total Hamiltonian of the system. This is the one. Here we have the kinetic energy of the electrons, the kinetic energy of the ions, electron-ion interaction, electron-electron interaction, ion-ion interaction. But in order to solve that very complicated problem, the approximation we are usually taking is the Born-Oppenheimer approximation, where we are neglecting the kinetic energy of the ions with respect to the kinetic energy of the electrons. So, according to that, the position of the ions is fixed. So, therefore, this position of the ions are the parameters in the Hamiltonian. We are fixing that position of the ions, and for that fixed position, we are calculating the wave function of the electrons. So let's consider that this wave function we have here, which of course depends on the electronic variables, the position variables, spin states, and do have that position of the ions as parameters, it's a variational wave function. And of course, we can calculate the energy associated to that variational wave function in the usual way, like that. And of course, as this either both this wave function and the Hamiltonian depend on this position vector of the ions, the energy is also going to depend on the position vector of the ions. So now we are going to apply the Feynman theorem. And according to the Feynman theorem, and considering that the parameters we have in the Hamiltonian are the position of the ions, then we could say that the derivative of the energy with respect to the position of the ion could be calculated in this way. We just need to do the average on this eigenstate, on this wave function, of the derivative of the Hamiltonian with respect to the position of the ion. We are taking a minus here for a thing we'll see later. Okay, we just need to do that. So what we are going to do? Now we are going to do the derivative of the position of the ions of the Hamiltonian. It's very easy to do in the sense that, as you have seen before, there is just two terms that have the position of the ions, this one and this one, the electron interaction and the ion-ion interaction. So it's very easy to do the derivative of these two terms with respect to the position of the ions. So doing that, you can see that this derivative, it has two terms, this one and this one. Okay, this one and this one. And the only remaining thing is taking the average. Taking the average of the last one, it's very easy in the sense that it's independent of the position of in the position of the electrons, so that the average is going to be just one, so it will remain like that. And taking the average of the first time is also quite easy in the sense that it only depends on the position vector of one electron. So when taking the average, it's very easy to see that this first contribution can be written this way, can be written as a function of the electronic density. So this is the expression we have for this left-hand side. And that's very easy to see that this expression here just corresponds to the force on a nucleus I, just as classical electrostatics would predict. So doing that, we are calculating the force on the nucleus, on the ion I. So what does it mean? That it means that considering the system is in a state which is a variational solution of the Hamiltonian, where it has this position of the ions as parameters, and the energy of that state is this one, which also depends on the position of the ions parameters, we can calculate the forces on the nuclei just doing the derivative of the energies with respect to the position of the ions. That's the way of doing calculating the forces on an ion. What basically means the following, that you have to calculate the energy for different ionic configurations, and from there you can take the derivative. And doing the derivative is going to give you the force on the ion. And the forces of the ion are really useful in the sense that the equilibrium geometries, you could find the equilibrium geometries of a molecule or solid. Just how can you do that? Just varying the position of the ions until we have that the forces are zero, or considering that expression until the derivative of the energy with respect to the position of the ion is zero. It's important also to remark that the function or the expression we have for the forces, it's also only depends on the electronic density for each set of nuclear positions. So this is a very straightforward way to calculate the forces on the ions, and actually it's very useful in order to, as I have said before, in order to calculate the equilibrium geometries of a solid, of a molecule, of different systems. So here we have an example of how useful is the Feynman Theorem, for example, to calculate the forces of the ions.